How do I turn off this flash? Okay, hello. Hello, guys. And this is a series that I'm going to do on calculus. Now, you'll see here all these topics listed here, and on every video, I will be marking which topics you need to know with these magnets. And so far, you should know up to I expect up to here. Now, you don't have to. But these are all the topics you have to know in this entire course. But right now, you really all need to know or be familiar with algebraic functions. So, if I had a function, and we're talking, this lesson's about limits. If I give you an algebraic function, x squared plus 1, and you should already know what this looks like by memory. It'll be a parabola shifted 1. And you find nothing fishy about it, no. By nothing fishy, you see no holes, nothing, no weirdness. And the way to check for fishiness, or we call it discontinuity, is you basically trace the function, and if there's some moment of time where you have to take your pen or pencil out while graphing it, it's obviously something's wrong with it. But what we call this is called a continuous graph function. There's nothing wrong. But we do have an idea that is useful, and it's so useful that it brings out all this. So, the idea of limits. And the best way to describe a limit is by using some function that does have something fishy. I'll write this one in factored form to easily see it. X plus 1 plus 2, minus 2, minus 2 over x. So, that's a function. And after this one, you'll know what these look like. So this is what the function looks like. Approximately, I'm just estimating, but nothing scaled. But this is the visual interpretation. And let me fix this just a little bit. There, I can see it. So now you trace along the graph, and it's just a line. And as soon as you get to this part, you have to jump to this part. That's an issue. That's a hole. That's what we call a hole. And it's right at x equals 2. And if you kind of notice, if you plug in x equals 2 on this function, it gets undefined. Now, this would be the point 3. Okay. Here's what limits kind of show us. They show you, well, go along the graph. Alright? Let's start with the left side first. And if you go along, you'll see, ooh, you get really, really close to 3, right? As you approach 2 from the left side, and you get really, really close to 2, this point right here is very close to 2, you notice that you get really, really close to 3. Really, really close to 3. And the same thing with the right side, right? You go along the graph, and you, oh, I'm really, really close to this hole. Well, that point right here is really, really close to 2, right? From the left side, from the right side, sorry. And you end up getting really, really close to 3. Well, both from the left and the right, you get really close to 3. And this is what a limit is talking about. The limit is basically saying what value is your function approaching. What are you approaching? What value are you approaching as you're getting really close to your x value? And the way you write this is the limit as x approaches 2 of your function. Now, we can specifically write this as that function right there. And you notice that, hey, if I get really, really close to 2, well, I'm approaching the value of 3. I'm getting really, really close to 3 right here. And that's from the left side. From the right side, same thing is happening. I'm getting really, really close to 2, but my value is getting really, really close to 3. Now there's a formal definition of a limit and there's an informal definition. I'm using the informal definition because it's easier to understand it that way. This diagram is actually almost demonstrating the formal definition, but the formal definition is just, I guess, it's too difficult and it'll mess with people's heads. It'll just make it confusing. I like to introduce the formal definition after some amount of time. Like in this course right here. It helps with the formal definition. So, just think about traveling on this line. And you're getting really, really close to your hole, or to your x value. So I'm getting really, oh, I'm there. I'm really close to 3. And from the right side, you go really, really close to 2. Oh, I'm approaching the value of 3. So the limit as x approaches 2 of this function from the left side and the right side, you get really, really, really close to 3. Let's view another example. Hopefully, all this is making sense. Okay, so what happens say, I'm not going to have a specific function right now, but if I were to be given this with another hole, like that, this one would, the potential one would be x squared plus 1, x minus 2. This one would look like that in factored form. So again, we're trying to figure out about this point 2 and this value right there. If we, and I'm going to just put 1, 2, 3, 4, 5, 6. You get the point. Okay, so if this is what we're approaching. We're approaching 2. We never get to 2. If we just jump right to 2, we're like, oh, it's undefined. We don't know. Well, if we approach 2, we can kind of see where we're going. So now we're going to say the limit as x approaches 2 of what our function is. So what are we approaching if we get really close to 2? So let's start with the left-hand side. Follow the function. Oh, we hit right there. So we got really, really close to 2, right? On the left side. Now on the right side, let's follow. Oh, we got really, really close. But this hole doesn't have a size. This hole is actually so small. So if we get really, really close, like that, we're getting close to 2, and the reason I had the hole big. Let's see. So we get close to 2 from both ends, and it looks like we're approaching the same value. And it's 5. So look at this. I'm running my fingers really, really close to 2. And they approach 1 value. And it's 5. So the limit as x approaches 2 of our function is 5. And that's all the examples I want to give you for our holes. Not really, I'm going to give you more. Now these ones are going to be more abstract. So what if we had this? This one's more abstract. Well, we're going to be approaching this value A. Or C, or whatever we call it. In the textbook it's a C. But I like to use A. So, okay. Let's start with the left. Let's follow the curve, And we're approaching some value here. And this is the x-axis somewhere. Right? We're approaching this value on the on the y-axis. I'm going to move my one finger along the curve and one finger that matches the x-axis. So I'm getting really, really close to, this value. Let's call it f of a. It's not f of a, I'm sorry. I'll just call it z. Yeah? Or L sub 1. We want to have L sub 1. Okay. Now if we approach, this is going to be hard to do, but if we go along here, along here. Get really, really close to this value right here. Really close from the right side. That's what we do. Now, another way of doing it is, hey, we're going from both sides and we're not adding at the same value. This one's clearly higher than this one. So, if you have a limit where you're approaching two different values from the left and the right, the limit doesn't exist. So this does not exist. It doesn't exist. Because a limit needs you to approach one value from the left and the right. The same value. How would this be fixed? It would be fixed if I did something like that. Then, both of these from the left and right would approach the same value. If my fingers meet, the limit has to exist. Now, some people are confused about the difference between f of a and the limit as x approaches a. These values don't have to be the same. This is saying what you're approaching. What function value are you approaching? What value are you approaching as you get really, really close to a? This is just saying what you get out of your function. So one example where they're not the same is if I had this weird example right here. This looks really weird. But it's saying, well, if I look at my y-axis, my x-axis, I'm interested in this point A, right? If I look at f of a, well, that's the point. That is f of a right here. When my thing is a, I'm not saying the whole is f of a. That's undefined. That's not there. That's where f of a is. That's the point. The limit as x approaches a, and the way you do this is you trace the graph with your fingers. Is if you get really, 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 really close to a, you're getting to this point right there. That is the limit. And it's the same from the left and right because they both meet. If they would have not met, then the limit wouldn't exist. So, in this case, the limit is not equal to the value of the function. And this importance will be discussed in the next section. We're going to go for one more example, different types of limits. Okay. So, if we have an asymptote, well, if you have an asymptote, what does it look like? It looks like this. This is not an accurate representation of this function, but it is a representation. So this is 1 over x, and there's an asymptote at x equals 0. Now let's follow along. Now we're going to use something special called one-sided limits. So a one-sided limit is when you have x approaching some value a from only one of the sides. So the negative means the left, plus right here means the right. And we're going to see what both of these equal, and if we see if the actual limit exists. And that'll be it. So let's just follow from the left. We trace the graph. Follow and follow and follow as we get really, really close to 0. We're approaching 0, but we're going down a lot. We'll be going forever down. And we'll never get to 0, but we'll get close to 0. And what happens here is we're getting really, really negative. Our values are going to get really big negatively. And we're going forever down. And we're still going to get closer to 0, but we're going to get really big numbers. And we're going to get the function approaches negative infinity. If we get really, 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 really close to 0, we're going to get something really negative, really big negative. Because the asymptote, let me extend this right here. It gets closer and closer and closer and closer and closer to 0, but it never gets to 0. At this point, we're really big negative. We're going to get really, really close to 0, and we're going to get really large negative numbers. So the function approaches negative infinity. And if you go from the right side, we're going to get really, 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 really big numbers if we get really close to 0 on the right side. So this will be infinity. Now you notice negative infinity and infinity are the same number or value. They're not values, but I'm saying they're not in the same place. Right? Your hands are touching metal. So the limit, actual limit, does not exist. We'll talk about more on limits, on one-sided limits, in the next section. Let's see if we have enough time to go over some problems. Okay, so does the limit exist, and what is it if it does? So I'm going to put up some examples. Okay. And I'll put the limit above. Think about these as I draw. So for the first one, we're going to say, what is the limit as x approaches a? What is the limit for the second one as x approaches a? They're going to do the same thing, but for this one, all the same. But I encourage you to solve these. And in the next video, I will give you the answers and explanations. So, again, for each of these, find the limit as x approaches a of the function, and if it exists, what is it? By the way, because I sound quiet, turn up the volume to max.